Hello everyone! In this video, I will be going over most of the reactions in which alkene is a starting reagent. I'll briefly highlight the reaction mechanisms and products formed in each reaction. Okay, let's go right into it. First off, we have the alkyl halide addition. In this reaction, a hydrogen halide reacts with the alkene to form an alkyl halide. Regioselectivity is predicted by Markovnikov's rule, where the halide adds to the more substituted carbon. This reaction, however, is not stereoselective since reaction proceeds via planar carbocation. One other reaction we learned is when HBr in the presence of peroxide and light will react with a free radical mechanism, resulting in anti-Markovnikov's regioselectivity. Okay, we can see the mechanism here. The first step of the reaction is an acid-base reaction. It starts with the protonation of alkene to generate the carbocation intermediate, with bromide being the leaving group. In the second step, attack of the nucleophilic bromide ion on the electrophilic carbocation creates alkyl bromide, which is the desired product. The conditions for hydration is H+ or H3O+ in the presence of water. So when treated with an acid, alkenes react to form alcohols. This acid can be H2SO4, which is a strong acid that has a good proton source. Regioselectivity is predicted by the Markovnikov's rule, with OH- adding to the more substituted side, and the reaction is not stereoselective. In the mechanism, first the alkene is protonated to form the carbocation intermediate by hydrosulfuric acid. Then the water serves as a nucleophile and attacks the electrophilic carbocation and creates an oxonium ion. In the final step, the conjugate base of H2SO4 deprotonates the water and forms the desired alcohol product, regenerating the catalyst as well, which is hydrosulfuric acid. Next up is hydrogenation catalysis. Hydrogenation happens in the presence of a metal catalyst such as platinum, and the reaction is not regioselective and always results in syn addition. As shown in the diagram, in the presence of metal catalyst, the hydrogen attached to its surface, and the double bond of the olefin is broken and also attaches to the surface. Hydrogen is then added one at a time to the same side of the alkene, therefore resulting in syn addition, and the resulting product is a saturated alkane. The next reaction is ozonolysis. The net reaction for this process is that the double bond is broken, and in its place the carbons form a double bond with oxygen. We're not required to know the mechanism, so I'll do a quick run-through. The mechanism begins by the formation of a cycloaddition product, which in turn cleaves to form an aldehyde and an aldehyde oxide. Rearrangement of these products show how it is possible to use these to form an ozonide. The ozonide then can react with diethyl sulfide to result in the products observed above and a sulfide byproduct. Here are the summaries for ozonolysis. In the presence of ozone and diethyl sulfide, the reaction results in a ketone and an aldehyde if one of the substituent on the carbon is a hydrogen. However, in the presence of water and protons, the aldehyde in the first equation becomes a carboxylic acid. This is an alternative method of forming an alcohol from an alkene. In the reaction, the mercury acetate attaches to the carbon with more substituents, and is then reduced in the second step with NaBH4. The reaction proceeds following Markovnikov regioselectivity, but is not stereoselective. The mechanism for the reaction on the previous slide is shown here. In the first step, the alkene double bond acts as a nucleophile and attacks the electrophilic mercury. At the same time, loss of the acetate ion forms a mercurinium ion. In the second step, water attacks the more substituted carbon from the backside, resulting in the breakage of the carbon-mercury bond. Then another water molecule or the acetate ion deprotonates the H2O group to give alcohol. In the reduction step, the hydride reduces the mercury, creating a carbon-hydrogen bond while breaking the carbon-mercury bond. This is a demercuration part of the process, and the mechanism is beyond the scope of this course. Hydroboration reduction is another effective way of obtaining a desired alcohol product. It follows the anti-Markovnikov regioselectivity in that the hydroxyl group attaches to the less substituted carbon. The first step of the mechanism is concerted, meaning that the CH bond and the CB bond are formed at approximately the same rate, and it follows a syn addition. And in the second step, with hydrogen peroxide and OH-, the stereochemistry is preserved. Treating an alkene with bromine or another halogen will result in a product containing two halide ions. This reaction proceeds from a bromonium intermediate. Bromine adds on opposite faces molecule, resulting in anti-stereochemistry. Because carbocations are not formed, the molecule does not have rearrangements. In the first step, the nucleophilic alkene double bond attacks a bromine atom, and the bromine atom also grabs onto the other electron-deficient carbon, resulting in the formation of a bromonium intermediate. Then, the other bromide ion attacks either carbon from the backside and breaks the carbon-bromine bond of the intermediate. The reaction proceeds via SN2 reaction mechanism backside attack, which results in the anti-stereochemistry. This reaction takes place in water and results in the breakage of a pi bond and the formation of a halohydrin. Halo refers to the halogen, and hydrogen refers to the alcohol that are added. The reaction results in anti-addition Markovnikov reaction, where OH adds to the more substituted carbon. The following diagram is the mechanism for the halohydrin formation. Nucleophilic pi bond attacks halogen molecule. The pi bond breaks in the process, while the lone pair of the bromine also attacks a carbon, forming a halogen bridge. The second halogen breaks away as negative halide, immediately surrounded by the solvent molecules. While halide is caged by water, another water molecule acts as a nucleophile and breaks the halide bridge from the backside. If it is asymmetric, water attacks the more substituted carbon. Yet another water molecule removes the excess H atom from the attacking H2O. The product is a halohydrin with halogen on one carbon and OH on its neighbor. Epoxidation is the synthesis of epoxides with peroxycarboxylic acid. So basically what peroxycarboxylic acid is just an extra oxygen to the equivalent carboxylic acid. A common reagent used is MCPBA. In the diagram, they actually made a mistake in that they mistaken the leaving group for the nucleophile, and the actual nucleophile is a highlighted carbon here on the double bond. So what happens is that when the carbons of the double bond serves as a nucleophile and attacks the electrophilic oxygen atom as marked in the red color in the diagram, and in the second step, this particular oxygen atom also acts as a nucleophile and attacks the other carbon atom, therefore forming an epoxide product. The Simon-Smith reaction takes place under the copper-zinc alloy, and the reaction breaks the double bond of the alkene and forms a cyclopropane. In the first step, the nucleophilic carbon-carbon double bond causes the loss of the iodide leaving group, and the electrons from the nucleophilic carbon-zinc bond being used to form the other carbon-carbon bond. This reaction is actually a concerted reaction that both new carbon-carbon bonds are formed simultaneously in the transition state. There are many ways to remove the double bond from an alkene and form a glycol with diol group. With OSO4 and H2O, as well as KMnO4 in basic conditions, the product formed is syn addition with the two OH groups attached to the same side. While if MCPBA is used as a reagent, the products formed follow anti-addition of the diol groups. Shown here is the reaction mechanism for the reaction of alkene with MCPBA. And on the lower right corner is the reaction of the alkene with OSO4. Thank you guys for watching and hope you learned something from the video.